We're back with part 2 of our week 4 notes. We are going to pick up with electron configuration again, and I would like to show you in this video how to use your periodic table to help you write correct electron configuration. So if you don't have the periodic table that you printed off handy, please pause the video and grab that, and we're going to make some additional marks on it. So looking at your note template, your fill-in notes handout, you see this periodic table that they've presented for you that is color-coded, and it is color-coded based on the sublevels that we talked about in the last video. Remember, the sublevels are the S, P, D, and F sublevels, and so this periodic table has been broken up into what they call blocks that correspond to these sublevels. We did go ahead and mark the period numbers on your periodic table, so let me just rewrite those. Remember that we said they correspond to that principal energy level, N equals, I can count apparently. Alright, so periods 1 through 7, that'll be helpful to us. Another thing that we need to do is to look at taking this block of helium right here. Helium, when we look at electron configuration, this box needs to be over here in the S block. So I'm just going to pencil that in, and that'll make a little bit more sense in just a minute. So on your periodic table, I would like for you to label the different blocks. So we have the S block is here, and the S block consists of just these first two groups, groups 1 and 2. So I'm going to just draw a dividing line right there. The block over here in the middle, we'll just go there first, that goes all the way from this first blue line to the second blue line. This is called the D block. And then at the very end, we have the P block. And the P block goes from the second blue line to the third blue line, so just this area. And then lastly, at the very bottom, we have the F block. And the F block consists of these two groups at the very bottom. So just like this color-coded periodic table, we have our periodic table broken up into the different blocks. And so what you can do then is, if you're looking at a particular element on the periodic table and you want to write the correct electron configuration, you can actually use your periodic table to help you with that. So if you think back to the rules that we learned, the first rule says that the electrons always fill the lowest energy level first. And so the lowest energy level will always be the 1s. So we're always going to start right here. So I'm just going to put a little star right here. And so no matter what electron configuration we write, we start right here in this first box. And on this periodic table that we're now using for electron configuration, we're going to let each box represent a place where there's one electron. Each of the boxes represent a place where there's one electron. So if you can kind of ignore all of these symbols for a moment and just look at the boxes themselves. And let me just jump into an example and see if I can help you figure this out. So let's say we want to write the electron configuration for nitrogen. So if we find the element nitrogen on the periodic table, and if you want to maybe just mark that with a pencil, I'll just put a little red dot on my periodic table. There's nitrogen. And so we want to write the correct electron configuration for nitrogen. So here's how you would go about doing that. We always start up here at the first box, the 1s box, and I'm just going to draw a line that kind of shows my path, the way that I get to nitrogen. So I'm going to go through hydrogen's box and helium's box, and as soon as I hit that blue line right there, I'm going to stop. So I had to pass through two boxes in the first energy level of the S block. So I'm just going to take a minute and write down what I just did. So that's the first energy level. We passed through the S block, and we went through two of those boxes. So 1s2. That's the beginning of that electron configuration. So if we look across here and we follow this all the way across, there are no other boxes on the first energy level. So that means we have to start back here to the second energy level. And so let's do that. We're going to go from the second energy level until we hit that blue line. And then we're going to stop and write down what we just did. So now we're at second energy level. We're still in the S block, and we had to go through 2 boxes. So it's 1s2, 2s2. All right, notice we got to this blue line, so we had to stop and change our letters, because when we get over here, now we're in the P block. We're still on the second energy level, but we're now in the P block. And so remember, we're on our way to nitrogen, so we're going to pick up right here until we get to nitrogen, and then we're going to stop. So we're going to write down what we just did. So we're still on the second energy level, but now we're in the P block, and we had to pass through 3 boxes to get to nitrogen. And so this would be the correct electron configuration for nitrogen: 1s2, 2s2, 2p3. So if you look closely at nitrogen, the atomic number is 7, which means there's 7 protons and also 7 electrons. So you can check to make sure this is correct by counting the number of electrons. Remember, this exponent is the electron. So there's 3, 4, 5, 6, 7. So this would be the electron configuration for nitrogen. If we wanted to write the orbital notation for the same thing, we can certainly do that. Remember, orbital notation uses a dash for the orbital. You have to tell where that orbital is located, and then we use arrows to show the electrons. So there's 1s2, 2s2, and remember, P has 3 orbitals, so we have to draw all 3 orbitals. And according to the rule, we're going to fill each orbital with 1 electron before pairing up. And so this would be the correct orbital notation for nitrogen: 1s2, 2s2, 2p3. All right, let's go through another quick example here, just to make sure you got it, and to show one way this periodic table method is going to be helpful. Let's try, let's see, what should we do? Let's try iron. Let's go all the way to number, what number is that? Number 26, iron. And so I'm just going to draw a dot there. Let me erase what I've done before. And we're going to be on our way to iron. And so again, we always start at the top at 1s. Every time we hit one of those blue lines, we're going to stop and write down what we did. So here we go. We're going through 1s. So we're doing iron. We just did 1s2. There's nothing else in the first energy level, so now we go back and do 2s2. Going all the way across to the next blue line. That takes us all the way across. So that's 2p, and there are 6 boxes there. Start over at 3s, pass through that. Follow it all the way over to 3p, pass through all of those, 3p6. And then we're at 4s, 4s2. Now here's where something changes. So our next block is the D block. And notice it's located on the 4th energy level. But there's something special about the D block. Whenever you get to the D block, when writing electron configuration, you take the N number, which is the period number, minus 1. N minus 1. So be sure and write that on your periodic table. Once you get to the D block, you have to subtract 1 from the period number. So instead of writing 4D, we're going to take 4 minus 1, which is 3. So we're going to call that 3D. And then we count 1, 2, 3, 4, 5, 6. 3D6. So this would be the correct electron configuration for iron. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So when you get to the D block, you have to take 1 away from the period number. All right, you'll get lots of practice with that in the textbook practice, so I'll move along. Our next topic here is about valence electrons, and the valence electrons are very important in the atom. In fact, the chemical properties of an element depend on the number of the electrons in the valence shell. The chemical properties depend on the number of electrons in the valence shell. The valence shell is the outermost shell, the one that's the farthest away from the nucleus, and these electrons are called valence electrons. The valence electrons determine the chemical properties of an atom, and so therefore are very important. You can determine valence electrons by looking at electron configuration. And so remember, we're looking for the outermost shell. So the electron shells are indicated by these numbers, big numbers in front. So we want to look for the largest number. So here the valence shell would be 2. And we can look to see that there are 2 electrons. So beryllium has 2 valence electrons. If we compare that to the periodic table, we can find beryllium. Erase some of the stuff. Here's beryllium. Notice it's in group 2. And so earlier we said that all elements in group 2 have 2 valence electrons. So that goes with this electron configuration as well. Looking at chlorine, if we wanted to tell the number of valence electrons, just looking at chlorine's electron configuration, again we find the valence shell, and so that's the number 3, and we count all of the electrons in the third energy level, and so therefore there are 7. And so that's just an easy way to look at the electron configuration and determine valence electrons. Elements in the same group have similar electron configurations. They all have the same number of valence electrons, so they're going to have very similar electron configurations. Elements in the same group have the same number of valence electrons. The group number, as I was saying earlier, the group number equals the number of valence electrons as long as we're talking about the main group elements. So here it says 1A through 8A. On a modern periodic table, that's groups 1 and 2 and 13 through 18. So when we look at these numbers, the ones place of the group number tells the number of valence electrons. So if we look, for example, let me scroll up. If we look at, let's look at one of these over here. If we look at, say, aluminum, we will look at aluminum. This is in group 13, and so we would look at the ones place, and that tells us the number of valence electrons. So the elements in group 13 all have 3 electrons, 3 valence electrons. There are a few exceptions to that, but for the most part. So the valence electrons can be determined by the ones place of the group number. One main exception is helium. Helium is in group 18, and going by the rule of using the ones place, you would think it would have 8 valence electrons, when in fact it only has 2. The chemical properties of a group are very similar because they have the same number of valence electrons. One thing that we can do with valence electrons is to draw something called an electron dot diagram, or electron dot symbol. And so in this symbol, the dots represent the valence electrons. Each dot represents just 1 valence electron. And so if you have 1 all the way up to 4 valence electrons, then you will just have a single dot around each side of the element. If you have more than 4 valence electrons, then the dots are paired. And so here's a few examples for you. You see hydrogen. Hydrogen has 1 valence electron, so it only has 1 dot. Carbon has 4 valence electrons, so notice there's a dot on each of the 4 sides, or carbon. And then oxygen here, this is the first one that has more than 4, so if I were drawing the electron dot structure for oxygen, I would put the symbol, and I would look at the periodic table and know that it has 6 valence electrons, so I would start putting the electrons around until I got the 4 all the way around, and then I would start pairing them up until I got to 6. And so it would look something like this. So electron dot symbols will become important to us when we start looking at different shapes. All right, the last thing we want to talk about is some patterns that we see on the periodic table. And these patterns are called periodic trends. Periodic trends. And the first trend that we're going to look at is atomic size. So the size of the atom, we're talking about how big the atom is. The size of the atom increases as I move down the column. The valence electrons are farther away from the nucleus, and therefore the size of the atom gets bigger and bigger and bigger. So here's an example. They've taken a little excerpt out of the periodic table. This is your halogens, fluorine, chlorine, bromine, and iodine. And the arrow is showing the size of the atom is getting larger as I move down the group. Fluorine has 2 energy levels, where iodine has 5 energy levels. So you can see that the size of the atom gets larger and larger. When we talk about going across a period, this says row. I think a better word would be period. We call the rows periods. As you go across the period, the size of the atom gets smaller. The size of the atom decreases as you go across the period. The number of protons in the nucleus is increasing, and this pulls the valence electrons in closer. So as I go down the group, the size increases. As I go across from left to right, the size decreases. The next trend that we're going to look at is something called ionization energy. Ionization energy is the energy needed to remove an electron from a neutral atom. So here's our neutral atom, sodium. It requires energy. Energy had to be put into the system, and an electron comes off, and we're left with something called an ion, a sodium ion. And so this trend that we're looking at is talking about the energy required to take that electron away. So the pattern that we see on the periodic table is that the ionization energy decreases as I go down the column. So as I move from top to bottom, the ionization decreases, which means that less energy is needed to remove an electron. So the trend is, as I go down the column, the ionization energy decreases. And then lastly, as I look across the period, the energy increases. Ionization energies increase across a period as the number of protons in the nucleus increases. So as I'm going across the period, it gets more difficult to remove the electron. So this is saying more energy is needed. to remove the electron, more energy. So these are just a couple of examples of patterns that we see on the periodic table. And again, you'll get more practice with this as you move through your modules.